Welcome to the channel and to this new journey into how the universe began step by step. If you enjoy calm, science-based stories about the cosmos, please remember to like the video, subscribe, and share it with someone who might enjoy it too. It really helps the channel grow, and I am very grateful for your support. Before we start, I would love to know a bit about you. What time is it for you right now, and where in the world are you watching from? Let me know in the comments below. Thank you for being here, and now let's begin. For a long time, the universe is imagined as quiet and eternal. Early astronomers mapped the sky with simple instruments and careful eyes, tracing the slow paths of planets and the steady patterns of stars. The sky above seems unchanging on human timescales, and the idea that the cosmos itself might have a birth or an end hardly appears in the language of science. Classical physics, developed to describe falling apples, swinging pendulums, and orbiting planets, settles into a comfortable picture of a universe in which matter moves through a fixed space. Space appears as a rigid backdrop. Time passes uniformly, and the universe is assumed to have always existed in roughly the same way. In this view, there is no first moment, only an endless stretch of past and future. The night sky supports this feeling. Stars rise and set, constellations return with each season, and even when new objects are found through better telescopes, they seem to fit into the same calm structure. Philosophers and scientists speak of an infinite, ageless universe, not because they have measured its age, but because nothing in their equations or observations yet demands a beginning. In the early years of the 20th century, this confidence begins to weaken. Albert Einstein develops the theory of general relativity, a new description of gravity in which mass and energy curve space and time. Gravity is no longer a force acting across emptiness, but a feature of the geometry of the cosmos itself. When Einstein applies his equations to the universe as a whole, he finds to his surprise that the simplest solutions do not allow a static universe. The equations tend to make the universe expand or contract. To protect the familiar idea of a universe that does not change on the largest scales, he introduces an extra term, a constant, that holds everything in balance. It is a mathematical patch that restores the eternal cosmos on paper, even though the underlying equations seem to resist this picture. Meanwhile, telescopes grow larger and more precise. Astronomers photograph faint smudges of light beyond the Milky Way and begin to suspect that these are separate galaxies rather than small clouds inside our own. At the Mount Wilson Observatory in California, Edwin Hubble measures the light from these distant systems. By examining how their light is stretched to longer, redder wavelengths, a change called redshift, he infers how fast they are moving away. The results are unsettling. The farther a galaxy is, the faster it seems to recede. The pattern is not random. It looks as though space itself is expanding, carrying galaxies away from one another like markers on an inflating surface. This is not an explosion from a central point, flinging matter into empty space. Instead, every region of space increases its distance from every other region without any edge and without any outside. The universe does not expand into anything. It is the network of distances that grows. Hubble's findings echo the suggestions already hidden in Einstein's equations, but now the evidence is observational. The old picture of a static universe becomes difficult to maintain. If everything is moving apart in a systematic way, then earlier in time, everything must have been closer together. Follow this idea far enough back, and the universe seems to converge into a state of enormous density and temperature, a beginning that is not a point in space, but a condition of all space. At first, many scientists are reluctant to accept such a conclusion. An eternal universe feels more neutral and less strange than one that starts abruptly. Alternative models are proposed to keep the universe ageless, including ideas in which new matter is continuously created as it expands, so that its overall appearance remains unchanged. For a while, the observations are not precise enough to rule these models out. The debate continues in journals and conferences with no clear winner. Gradually, however, more detailed measurements accumulate. Counts of distant galaxies, studies of their distribution in space, and the discovery of a faint, uniform glow of microwave radiation that seems to bathe the entire sky all point toward a universe that was once far hotter and denser than it is now. The expanding universe picture now carries not just theoretical weight, but a growing body of observational support. The calm, eternal description of classical physics gives way to a more dynamic story, in which the cosmos has a history, a childhood, and perhaps even an origin that can be studied. As astronomers refine their estimates of how fast the universe expands, they begin to infer an approximate age for the cosmos by running the expansion backward in time. Early calculations sometimes suggest an age younger than the oldest known stars, a clear clash that signals gaps in understanding. Either the measurements are incomplete or some part of the physical picture is missing. Such tensions underscore how fragile the new framework still is and how much remains to be learned about the true behavior of space and time on the largest scales. Yet even with these uncertainties, the direction of the evidence is difficult to ignore. The universe behaves as though it has expanded from a denser state, and traces of that state appear to linger in the background radiation and in the way galaxies are arranged across the sky. The shift from an ageless cosmos to a universe with a possible starting moment marks more than a change in theory. It forces science to confront the idea that the universe itself might have evolved from something simpler and more compact, and that the traces of that early state could still be visible in the sky. The old certainty of an eternal universe fades, replaced not by a complete explanation, but by a deeper mystery about how the story truly starts. The recognition that the universe is expanding transforms astronomy from a descriptive craft into a forensic investigation of cosmic history. Once the pattern of recession speeds and distances is established, every patch of sky becomes a record of how things used to be, because light takes time to travel. Galaxies that are very far away are seen as they were when the universe was younger, so a deep image is not just a map across space, but a slice back through time. Astronomers begin to think of the sky as an archive. By reading its signals carefully, they hope to reconstruct how the universe evolved from that initial dense state into the vast structure seen today. The first clear signal is the systematic redshift of galaxies. When the light from a distant galaxy is broken into a spectrum, dark lines appear where atoms in the galaxy absorb specific colors. In a laboratory on Earth, those lines occur at well-known wavelengths. In the distant galaxy, the same pattern appears shifted toward the red end of the spectrum. The amount of shift reveals how much the light has been stretched by the expansion of space during its journey. This simple, repeatable measurement links a piece of distant matter to a precise motion. Many galaxies are measured. The trend is unmistakable. On large scales, everything recedes from everything else. This observation fits naturally into the growing picture of a universe that began in a much hotter, denser condition. If space has been stretching over billions of years, light that set off when the universe was young will now be stretched into longer wavelengths. Warm light becomes cool light. Blazing radiation becomes a faint glow. Researchers reason that if the hot early universe really existed, its leftover radiation should still fill space, though now so cooled and stretched that it would be invisible to human eyes. Dedicated instruments might detect it as a nearly uniform background coming from all directions. For a time, this remains a theoretical prediction. Then, in the mid-1960s, a pair of radio engineers working on a communication antenna encounter an unexpected source of noise. No matter where they aim the device, a persistent hiss contaminates their measurements. They check their equipment, remove sources of interference, and even clean out nesting material left by birds inside the antenna. The noise remains. Eventually, it becomes clear that the signal does not come from the instrument or from the local environment. It arrives uniformly from the sky itself. Soon, physicists recognize that this background matches the predicted radiation from a hot early universe that has expanded and cooled. What appears as a faint microwave hiss is in this interpretation the afterglow of the Big Bang light released when the universe was much younger and denser, now stretched by expansion into microwaves that fill all of space. This discovery turns a speculative picture into a more concrete story. The universe seems to remember its own childhood, not only in the motions of galaxies, but in this all-pervading glow. Decades later, space missions are launched to map this background in detail. One spacecraft measures the temperature of the sky and microwaves across all directions with remarkable sensitivity. On the largest scales, the radiation appears almost perfectly uniform, implying that the early universe was extremely smooth and even. But with careful analysis, tiny irregularities emerge temperature differences of only a few parts in many thousands. These minute variations are crucial. They represent regions that were slightly denser or less dense than average in the young universe. Over time, gravity would amplify these small differences, drawing matter into clumps that eventually become galaxies, clusters, and the large-scale web of structure. In this way, the faint mottling of the microwave background acts as a blueprint for everything that forms later. The pattern is strikingly consistent with a universe that has expanded from a hot beginning, yet it also raises puzzles. The background is smooth over vast regions that, according to simple calculations, should not have been able to exchange light or information before the radiation was released. Different parts of the sky that are now widely separated seem to have almost exactly the same temperature, even though they should never have been in contact in a straightforward expansion scenario. This is known as the horizon problem. Why is the universe so uniform on large scales when distant regions appear to have had no opportunity to coordinate their conditions? Another puzzle is the near flatness of space on observable scales. Measurements of the cosmic background, combined with counts of galaxies and detailed studies of large structures, suggest that the geometry of the universe is very close to Euclidean meaning, that parallel lines remain parallel, and large triangles have angles that add up to almost exactly a straight angle. In general relativity, this flatness depends sensitively on the total energy content of the universe. Any small deviation in the early universe would grow over time, leading to either a rapid recollapse or a runaway expansion that prevents structures from forming. The fact that the universe today appears so finely balanced suggests that something in the earliest moments set conditions with extraordinary precision. As more data arrive from ground-based observatories, balloon experiments, and space telescopes, the basic picture of an expanding universe with a hot origin grows more secure. Yet each improvement and measurement introduces fresh details that must be understood. Slight asymmetries in the background, subtle alignments of temperature features on the largest scales, and small tensions between different ways of estimating cosmic parameters hint that the story may not be completely settled. The sky offers clear signals, but it also carries a residue of anomalies that keep theorists alert. The expanding universe reveals itself not as a simple narrative, but as a layered record. Galaxies at different distances show different stages of evolution. The microwave background preserves a snapshot of an even earlier era. In principle, by combining these strands, science can reconstruct a step-by-step account of how the cosmos grew from near uniformity into its present complexity. In practice, every reconstruction depends on assumptions about what happened in the very first instance before the background radiation was released, when the known laws of physics are pushed to their limits. Observations tighten the constraints, but they also underscore that the most fundamental pieces of the story remain partly hidden, encoded in patterns that instruments can measure, yet not fully explain. As the evidence accumulates that the universe expanded from a hot, dense beginning, attention turns to an even earlier stage, one that leaves no direct light to observe, but imprints its influence on everything that comes after. The smoothness of the cosmic background radiation across wide regions of the sky and the near flatness of space on large scales hint that something dramatic happened in the first tiny fraction of a moment. Ordinary expansion alone does not easily explain why regions that could never have exchanged light end up with almost identical temperatures, or why the overall geometry sits so close to the delicate balance between rapid recollapse and runaway thinning. To address these puzzles, theorists propose that the early universe passes through a brief phase of extremely rapid expansion called inflation. In this picture, space itself does not merely grow steadily. It swells at an accelerating rate, doubling its size again and again in a time so short that normal language struggles to convey it. During this inflationary episode, distances between points grow so fast that regions which were once in close contact are stretched far beyond each other's horizons. Before inflation, the matter and radiation that now occupy opposite sides of the sky could have mixed, traded energy and settled into a common temperature. When inflation ends and the expansion slows to a more moderate rate, those regions are frozen apart, looking uniform, even though they can no longer communicate through light. In this way, the surprising smoothness of the cosmic microwave background becomes a natural outcome of a very early period of intimate contact, followed by extreme stretching. Inflation also offers a way to understand the near flatness of space. If a balloon is only slightly inflated, Its surface looks curved even on small scales. But if it is blown up much more, the same patch appears flatter to a small observer walking across it. Likewise, if the early universe undergoes a huge amount of expansion, any initial curvature becomes diluted. Space begins with whatever shape it has, but the rapid swelling makes it look flatter and flatter within any reachable region. By the time inflation ends, the observable universe can appear almost perfectly flat without requiring a finely tuned starting condition. The idea is simple to state, yet the details involve deep physics. Inflation is usually described as the result of a field, a quantity that has a value at every point in space carrying a certain form of energy that behaves differently from ordinary matter or radiation. While this field sits in a high-energy state, its presence causes space to expand at an accelerated rate, somewhat like the way a stretched elastic sheet might snap outward when tension is released. As the field slowly changes, the conditions become unstable, and inflation eventually ends in a kind of reheating. The stored energy converts into a hot mixture of particles and radiation, seeding the familiar hot Big Bang phase that continues from there. What makes inflation especially interesting is that it does not simply smooth out the universe. It also introduces the right kind of small irregularities. At the smallest scales, physics allows tiny fluctuations to exist, brief departures from uniformity that wink in and out of existence. During inflation, these quantum variations are stretched from microscopic sizes to cosmic scales. Regions that are slightly more dense or less dense than average are pulled apart, imprinted as small variations in the energy density of space. After inflation ends and the universe continues to expand more gently, these frozen fluctuations become the seeds of future structure. Eventually, matter falls into the slightly denser regions, reinforcing them, while slightly emptier regions become the beginnings of cosmic voids. The pattern of hot and cold spots, seen in the microwave background, appears to match this general picture, small, nearly random differences, with a statistical distribution that aligns with inflationary expectations. Large-scale galaxy surveys, which map the positions of millions of galaxies, also show a subtle preferred scale in how galaxies cluster, a kind of faint ripple pattern that echoes the acoustic waves in the hot plasma of the early universe. Inflation provides a natural setting for such features, turning initial quantum fluctuations into the starting points for later sound waves and structures. Yet for all its successes, inflation is not a complete or final answer. There are many possible versions of the inflationary field and its potential energy landscape, each with different detailed predictions. Observations of the cosmic background and of large-scale structure can rule out some models and favor others, but the space of options remains wide. Some formulations of inflation suggest that the rapid expansion never fully ends everywhere, but continues in distant regions, giving rise to a picture in which our observable universe is just one bubble within a larger, endlessly inflating space. In such scenarios, different bubbles could have slightly different physical properties, different values of fundamental constants, or even different numbers of large spatial dimensions. This raises the speculative possibility of a multiverse, a vast collection of pocket universes separated by inflating space, each with its own version of cosmic history. These ideas are intriguing, but they rest on extrapolations of known physics into regimes where it has not been tested. Moreover, inflation does not completely remove the need for initial conditions. It shifts the question. Instead of asking why the universe began in such a special state, one asks why the inflationary field had the right properties to trigger the rapid expansion and then to stop. The theory explains certain features, but opens new lines of inquiry about the deeper origin of those features. There is also the challenge of connecting inflation with a more fundamental framework that includes both quantum mechanics and general relativity in a consistent way. Near the very beginning, when densities and curvatures are extreme, neither theory alone is expected to be sufficient. A full theory of quantum gravity still under development would be needed to describe the earliest instance with confidence. Without it, any story about times earlier than the end of inflation remains provisional. Observationally, scientists search for more clues. One important target is the pattern of polarization in the cosmic microwave background. Certain shapes in this polarization could be signatures of primordial gravitational waves ripples in space-time generated during inflation and later imprinted on the background radiation. Detecting such a pattern would provide strong support for an inflationary phase and would give direct information about its energy scale. Experiments on high mountain tops and observatories at the South Pole, along with future satellite missions, scan the sky with increasing sensitivity, looking for these subtle signals. So far, no definitive detection has been made, but upper limits already constrain many inflationary models, narrowing the field of plausible scenarios. Even without firm answers, the study of inflation transforms how the beginning is imagined. Instead of a simple undefined starting point, there is a possible sequence, an unknown quantum gravitational regime, followed by a burst of inflationary expansion, which in turn hands off to the hot Big Bang phase, described by well-tested physics. Each stage leaves traces in the next, so that by carefully reading the sky today, science attempts to infer not only how the universe evolved, but also how its earliest instance may have unfolded. The overall picture remains incomplete, but within the patterns of radiation and structure, there is a growing sense that the first moments were not featureless, but rich with processes that continue to shape the cosmos long after they have ended. Once the early universe enters the hot Big Bang phase after inflation ends, it is filled with an intense bath of radiation and a crowded sea of particles and antiparticles. Temperatures are so high that matter and antimatter appear readily from energy and just as readily annihilate back into light. Under such extreme conditions, the distinction between matter and radiation is blurred. Particles emerge from collisions, exist for brief intervals, and disappear again. According to the basic symmetries of known physics, matter and antimatter should be produced in nearly equal amounts. For every particle, there is a corresponding antiparticle with the same mass, but opposite charge or other quantum numbers. When a particle meets its antiparticle, they annihilate, leaving behind pure energy. In an exactly symmetric universe, this process would lead to near complete cancellation. After the universe expands and cools, almost no matter would remain, only a thin soup of photons, with perhaps a trace of exotic relics. Yet, the universe that exists today is not empty radiation. It is filled with stars, planets, gas clouds, dust, and all the structures that arise from ordinary matter. Antimatter is rare and usually found only in high-energy processes or in specialized laboratory experiments. This contrast implies that in the early universe, something broke the balance. For every enormous number of matter particles and antiparticles that annihilated each other, a small surplus of matter remained. The sample script describes this as roughly one extra matter particle for each large batch of matter and antimatter. That tiny excess is enough to account for all the atoms now present in galaxies and in intergalactic space. The mystery is how such an asymmetry arose from conditions that might at first appear neutral. To investigate this question, scientists explore the detailed behavior of fundamental interactions at high energies. They find that certain processes in particle physics do not treat matter and antimatter in exactly the same way. This subtle difference is called charge parity violation. In some decays of unstable particles, the probabilities for a process and its mirror image involving antiparticles do not match perfectly. Over many events, this unevenness can favor the production of matter over antimatter by a small margin. In the early universe, where energies and densities are extreme, such tiny imbalances could be magnified into a lasting asymmetry. For a mechanism to generate the observed surplus of matter, several conditions must be met. There must be reactions that change the number of particles carrying baryon number a quantity associated with protons and neutrons. There must be violations of charge parity symmetry, and the universe must pass through states that are out of thermal equilibrium so that certain processes do not simply undo the asymmetry as fast as it is created. These general requirements described in broad terms, without relying on formalism, guide theoretical models of how matter came to dominate. One approach, sometimes called baryogenesis, imagines that at very early times, exotic heavy particles decay in ways that slightly favor matter over antimatter. Another route involves processes related to the electroweak interaction where the forces that govern radioactive decay and electromagnetism are unified at high temperatures. In some versions, as the universe cools, and this unified interaction splits into distinct forces, transitions in the fields involved could produce a net baryon number. There are also models where the asymmetry first appears in the lepton sector associated with particles like neutrinos and is later transferred to baryons through certain reactions. These possibilities differ in details, but each aims to link a small violation in microscopic processes to the large-scale fact that matter fills the cosmos. Observationally, the existence of a matter-dominated universe is clear. Experiments at particle accelerators have measured charge parity violation in certain systems, confirming that nature does distinguish between matter and antimatter in subtle ways. However, the amount of asymmetry seen in these laboratory processes is not yet sufficient within the simplest calculations to explain the full cosmic matter excess. This gap suggests that either there are additional sources of symmetry breaking not yet discovered, or that the early universe passed through conditions that enhance the effect. The cosmic microwave background and the abundances of light elements provide indirect constraints. The background radiation with its precise spectrum and slight fluctuations reflects the density of matter and radiation when it was released. The relative amounts of hydrogen, helium, and trace elements like deuterium and lithium produced during the first minutes in a process called Big Bang nucleosynthesis depend on the balance between the number of protons, neutrons, and photons at that time. Both of these observational pillars point to a universe in which the matter-to-photon ratio is small but non-zero, consistent with a large number of annihilations leaving behind a tiny residue. The numerical value of this ratio can be inferred with increasing precision, but the underlying reason why it takes that specific value rather than another remains unknown. Conceptually, the idea that almost everything cancels and only a slight excess survives is both simple and unsettling. It means that every familiar object from a grain of dust to a galaxy cluster owes its existence to a minor imbalance in early particle processes. If the asymmetry had been slightly smaller, the universe would be nearly empty of matter. If slightly larger, it might have formed very differently, with nuclear reactions in the early minutes consuming more hydrogen and altering the later formation of stars. This sensitivity raises questions about whether the observed value is a random outcome, a necessity imposed by deeper laws, or a selection effect among many possible universes in a wider multiverse. The matter-antimatter asymmetry also has implications for how time is understood in fundamental physics. Many basic equations are symmetric under reversal of time, at least at the level of pure mathematics. However, processes that violate charge parity symmetry when combined with other considerations imply a related violation of time reversal symmetry. In this sense, the dominance of matter is tied to a preferred direction of time in the microphysical world beyond the familiar arrow defined by increasing entropy. The early universe is not only hot and dense, it is also a stage on which these asymmetric processes play out quietly, selecting one branch of possibility over another. In practical terms, the presence of matter without corresponding antimatter defines the boundary conditions for all later cosmic evolution. As the universe cools below the threshold where particle pair production from the radiation bath becomes efficient, annihilations cease to create new pairs. The remaining matter, both baryonic and possibly non-baryonic, continues to interact gravitationally, feeling the influence of radiation but no longer in equilibrium with it. The surplus baryons form the raw material for the first nuclei atoms, gas clouds, stars, and planets. The absence of a comparable antimatter component means that large-scale annihilation events do not prevent structure from forming and persisting. Searches for regions of space dominated by antimatter have so far found no convincing evidence on galactic or larger scales, reinforcing the picture of a universe where matter's small early victory is complete on observable distances. Yet every attempt to explain precisely how this victory was achieved remains incomplete. The parameters of particle physics measured today may be remnants of processes at energies far beyond current reach. The early universe acts as a natural laboratory for such conditions, and its large-scale properties reflect the outcomes. As measurements of cosmic background radiation, galaxy distributions, and high-energy reactions improve possible scenarios for matter generation are tested and refined. Some are ruled out, others remain in contention, and new ideas continue to appear. The core fact persists in the first instance. After the hot Big Bang, the balance between matter and antimatter is tipped by a barely perceptible amount, and that tiny shift defines the material content of everything that follows. Behind this apparently simple statement lies a complex network of interactions, symmetries, and violations that tie the behavior of minute particles to the existence of stars and galaxies, hinting that the origin of matter is one of the deepest links between fundamental physics and cosmic history. still waiting for a complete explanation. In the first instance, after inflation ends, the universe is not only hot and dense, it is also governed by forces that do not yet look like the distinct interactions later measured in laboratories. At familiar energies, four fundamental forces are recognized: gravity, which shapes the motion of planets and galaxies; electromagnetism, which governs light and the behavior of charged particles; the strong interaction which binds quarks into protons and neutrons and holds atomic nuclei together; and the weak interaction which drives certain kinds of radioactive decay and plays a role in the reactions inside stars. Today, these forces appear different in strength and range, and they operate through different kinds of particles. In the extreme conditions of the early universe, however, their roles may have been less sharply divided. As temperature rises, the characteristic differences between forces blur. Theories suggest that at very high energies, some of the forces merge into unified interactions described by a single mathematical framework. As the universe cools, this unification breaks down in stages, a process known as symmetry breaking. The term symmetry here refers not to a visible shape, but to a set of rules that treat different states or directions in a similar way. When a symmetry holds, certain transformations leave the system unchanged. When it breaks, some outcomes become favored over others, and distinct forces emerge. In broad outline, the story runs as follows. At the highest energies, far beyond anything that can be produced in current accelerators, gravity might join the other interactions in a still unknown unified description. As the universe expands and cools slightly, this primordial unity gives way to a separation in which gravity decouples from the rest, leaving a still unified, strong electro-weak interaction. Later, as temperatures drop further, the strong interaction splits from the electro-weak. Finally, at energies more accessible to experiment, the electroweak force itself breaks into the electromagnetic and weak interactions, giving rise to the familiar distinction between light and radioactivity. Each breaking of symmetry can be compared loosely to a phase change like the freezing of water, though the details are more abstract. A field that once had a perfectly symmetric configuration settles into a new arrangement in which some directions in an internal space are preferred. The vacuum state, which can be thought of as the lowest energy configuration of fields, changes character. Particles gain mass through their interactions with these fields, and the strengths and ranges of forces shift to their present values. In the early universe, these transitions take place as the temperature crosses certain critical thresholds. The electro-weak symmetry breaking, for example, occurs when the universe is still extremely young and hot by everyday standards, yet cool compared to its initial state. Before this event, electromagnetic and weak processes are interchangeable aspects of a single interaction. After it, photons become massless carriers of the electromagnetic force, while the particles associated with the weak interaction acquire mass and become short-ranged. The consequences of these changes ripple across cosmic history. The behavior of particles in the primordial plasma, the rates of reactions that build light nuclei, and the pattern of fluctuations imprinted on the cosmic microwave background all depend in subtle ways on how these forces settle into their distinct roles. Grand, unified theories which aim to combine the strong and electro-weak interactions into a single framework at very high energies predict additional phenomena. Many of these models imply the existence of heavy particles that no longer exist in the present universe, except possibly as extremely rare relics. Some versions predict that protons, though very long-lived, are not absolutely stable, but can decay over immense timescales. Others suggest that isolated magnetic charges called magnetic monopoles might be produced in abundance during the early symmetry-breaking transitions. These monopoles have not been observed, and their absence in the present-day sky becomes another clue. Inflation itself, by stretching space enormously, could dilute any monopoles formed before it to such low densities that they are effectively impossible to detect, turning a potential problem into a feature. Searches for proton decay are ongoing in large underground detectors filled with pure water or other material shielded from cosmic rays by thick layers of rock. So far, no convincing signal has been seen, pushing the predicted lifetime of the proton to values far beyond earlier expectations and ruling out some grand, unified models. In this way, cosmic history and laboratory experiments remain tightly linked. The pattern of surviving matter and the absence of certain exotic relics place strong limits on the possible paths the early universe could have taken as its forces differentiated. The strengths of the forces today appear finely balanced. The strong interaction is just powerful enough to bind quarks into stable protons and neutrons without crushing them into heavier combinations that would rapidly decay. Electromagnetism is strong enough to hold electrons in orbit around nuclei-forming atoms, but weak enough that atoms in a solid or gas can interact in varied ways, allowing complex chemistry. The weak interaction is feeble compared to the strong and electromagnetic forces, but not so feeble that nuclear reactions in stars stall. Gravity is extraordinarily weak between individual particles, yet dominates on large scales because it is always attractive and accumulates with mass. Small changes in these relative strengths could lead to very different universes, with nuclear reactions running too fast or not at all, with no stable hydrogen or with no stable carbon and oxygen. The fact that the actual values fall in a narrow range that permits long-lived stars and complex structures invites questions about whether this balance is an inevitable consequence of deeper principles or one outcome among many possibilities. In speculative frameworks that include a multiverse, different regions of a larger reality might realize different values of these constants. In many such regions, the combination of forces might not allow for galaxies, stars, or complex chemistry. The set of parameters observed in the known universe would then be one member of a broad distribution, selected not by design, but by the requirement that structures capable of observing them conform. This anthropic reasoning remains controversial and sits at the boundary between physics and broader reflection, but it illustrates how the separation of forces in the early universe connects to questions about why the cosmos has the kind of structure it does. On the observational side, the imprints of symmetry breaking are more indirect than the direct signals from the background radiation. Nevertheless, they leave traces. The pattern of particle masses and mixings measured in accelerators reflects the structure of the underlying fields. The behavior of the early plasma, as inferred from the microwave background and from the abundance of light elements, constrains how the forces acted when the universe was seconds and minutes old. Future measurements, such as more precise studies of neutrino properties or searches for rare decays, may reveal additional aspects of the unification story. Theoretical work continues to explore how different symmetry-breaking sequences would influence cosmic evolution and whether there are subtle signatures that could distinguish between them. At the same time, attempts to combine quantum mechanics with gravity in candidate theories of quantum gravity, such as those based on extended objects or discrete space-time structures, suggest further layers of unification and breaking at scales where current observations offer little guidance. In the narrative of cosmic beginnings, the separation of forces is one of the key transitions. From an early state in which interactions may have formed a single elegant structure, the universe cools into a phase where complexity becomes possible. The rules that govern particles and fields become less symmetric but more varied, allowing for the rich tapestry of phenomena seen in both the micro-world and the large-scale cosmos. Behind the familiar list of four forces lies a deeper history of unity and differentiation that is only partly understood, hinting at a more comprehensive framework that might one day explain why the universe's basic interactions are as they are and not otherwise. In the young universe, after the initial burst of inflation and the earliest symmetry-breaking events, the cosmic contents are still far from the familiar atoms and structures of later times. Instead, space is filled with a hot, dense plasma of fundamental particles and radiation. Quarks, leptons, gluons, photons, and neutrinos move in an energetic crowd, colliding, frequently appearing and disappearing as energy converts into matter and matter converts back into energy. Temperatures are so high that particles with significant mass can be produced readily from the radiation bath. In this regime, individual identities are fleeting, yet the overall mix follows rules set by the expanding background and the evolving forces. As the universe expands, its temperature drops. This cooling is not due to contact with an outside environment. It is a direct consequence of expansion itself. When space stretches, wavelengths of radiation lengthen and the average energy of photons decreases. Particle collisions become less energetic on average, making it harder to sustain certain species that require high thresholds to be produced. At first, quarks and gluons move almost freely in a deconfined state, similar to the quark-gluon plasma studied in heavy ion collisions on Earth, but at far greater scales. As temperatures fall below a critical level, the strong interaction confines quarks into bound states, forming hadrons. Hadrons are composite particles made of quarks held together by gluons. Among the many possible combinations, some are baryons composed of three quarks, such as protons and neutrons. Others are mesons, made of a quark and an antiquark pair. In principle, a wide variety of hadrons can form, but their stability depends on the masses of the quarks involved and the details of the strong interaction. Many hadrons are short-lived and quickly decay into lighter, more stable species. In the early universe, this transition from a quark-gluon plasma to a hadron gas is rapid on human timescales, though it occupies a finite interval in cosmic history. As confinement proceeds, the population of free quarks dwindles, replaced by a swarm of hadrons constantly interacting, colliding, and decaying. Protons and neutrons, being among the lightest baryons, emerge as key survivors. Their relative abundances are set by a balance between reactions that convert one into the other, involving electrons, positrons, neutrinos, and antineutrinos, and by the changing temperatures and densities as the universe continues to expand. At high temperatures, these conversion reactions proceed efficiently in both directions, keeping protons and neutrons in near equilibrium. As the universe cools past a certain point, the reaction rates slow compared to the rate of expansion. At that moment, the ratio of neutrons to protons effectively freezes out. Freed neutrons are unstable with a mean lifetime of about a quarter of an hour. Over time, in the absence of binding, they decay into protons, electrons, and neutrinos. In the early universe, however, not all neutrons have time to decay before they are captured into nuclei. A window opens lasting only a few minutes, during which conditions are right for nuclear synthesis on a cosmic scale. This epoch is known as Big Bang nucleosynthesis. During this period, protons and neutrons collide and, through a series of reactions, build light nuclei. The simplest and most abundant nucleus formed is that of deuterium, consisting of one proton and one neutron. Deuterium can then combine with additional protons or neutrons to create helium-3, helium-4, and a small amount of lithium and other light isotopes. The efficiency of these processes depends sensitively on the density of baryons, the expansion rate, and the temperature. If the universe were denser in baryons, nuclear reactions would proceed more efficiently, consuming more deuterium and helium and producing heavier elements. If it were much less dense, too few collisions would occur and very little helium would form. The observed abundances of hydrogen, helium, and deuterium in the present universe match the pattern expected from nucleosynthesis with a particular baryon density, providing strong support for this early nuclear phase. By the end of Big Bang nucleosynthesis, most neutrons that have not decayed are bound in helium-4 nuclei each, containing 2 protons and 2 neutrons. The resulting composition is simple, yet influential. About 3/4 of the baryonic mass is in hydrogen nuclei, essentially single protons, and about 1/4 is in helium, with trace amounts of deuterium and lithium. The universe, only minutes old, already carries a chemical imprint that will shape the formation and evolution of stars billions of years later. After nucleosynthesis ends, the universe remains too hot for electrons to bind stably to nuclei. Instead, it is filled with a plasma of positively charged nuclei and free electrons with photons scattering frequently off the charged particles. Light cannot travel far without interacting. The universe is opaque, more like the interior of a star than the transparent space seen today. As expansion continues and the temperature drops further, the energies of typical photons fall below the binding energy of the simplest atoms. Eventually, conditions allow electrons to combine with nuclei and remain attached. This process, called recombination, turns the plasma into a gas of neutral atoms. With far fewer free charges to scatter from photons, begin to travel freely over enormous distances. The light released around this time is what is now observed as the cosmic microwave background, stretched by expansion from visible and infrared wavelengths to microwaves. The first atoms to form are mostly hydrogen with helium and trace species following similar paths. The universe at this stage can be pictured as a vast dark volume filled with neutral gas and a background glow of radiation. The term dark age is used to describe the interval between recombination and the ignition of the first stars. During this time, no luminous objects yet exist to produce new light at shorter wavelengths, and the neutral hydrogen gas efficiently absorbs many kinds of radiation. Yet, despite its quiet appearance, this era is crucial. The density fluctuations imprinted earlier by inflation and recorded faintly in the microwave background now begin to grow under the pull of gravity. Regions that are slightly denser than average attract more matter, becoming denser still, while underdense regions lose matter and become emptier. The neutral gas responds to these subtle variations, flowing slowly toward the emerging gravitational wells. On large scales, the interplay between pressure, gravity, and expansion shapes the formation of structures. Dark matter, a non-luminous component inferred from its gravitational effects, plays a central role by providing additional mass in which ordinary gas can collect. Though its exact nature remains unknown, dark matter contributes the majority of the universe's matter density, deepening potential wells and accelerating the collapse of gas in certain regions. Without dark matter, calculations suggest that the small initial fluctuations seen in the microwave background would not have grown quickly enough to form galaxies and clusters by the present day. On smaller scales, within collapsing regions, gas dynamics become complex. As gas falls inward, it is heated by compression and by shocks from colliding streams. Radiative processes allow some of this heat to be lost, enabling further collapse. Over time, dense clumps form within filaments and knots of the cosmic web, the large-scale pattern that will eventually host galaxies, groups, and clusters. The seeds planted in the early plasma thus evolve into increasingly structured forms, guided by gravity, but constrained by the initial conditions set by the Big Bang and its immediate aftermath. The story of quarks becoming hadrons, hadrons assembling into nuclei, and nuclei capturing electrons to form atoms, is in one sense straightforward. It follows known physics tested in laboratories and reactors scaled up to cosmic dimensions. Yet, even here, open questions remain. The precise values of particle masses, coupling strengths, and fundamental constants determine the timing and efficiency of each step. Small changes in these quantities would alter the balance, potentially preventing the formation of stable nuclei or shifting the chemical mix in ways that might hinder later structure formation. Observations of the cosmic microwave background and of primordial element abundances continue to refine these parameters, drawing a more detailed picture of how a featureless early plasma gave rise to the first building blocks of matter. In this way, the transformation from a hot soup of quarks and gluons into a cool gas of hydrogen and helium marks another key transition in the universe's early history, setting the stage for the long dark interval in which gravity patiently amplifies small irregularities into the first stars and galaxies. After recombination, the universe enters a long interval in which no new bright sources yet exist. Space is filled with neutral hydrogen and helium gas, thin but pervasive, and with the cooling glow of the background radiation. Photons from this radiation now travel freely, no longer scattered at every step by free electrons, but their wavelengths are stretched by the expansion of space, shifting them into the microwave range and beyond. The overall scene, if it could be seen, would not resemble the rich star fields known from later times. There are no stars, no galaxies with bright cores, no clusters sending out powerful radiation. Instead, there is a nearly uniform gas and a faint bath of light whose temperature gradually drops as the universe expands. This era is often called the cosmic dark age, not because there is no radiation at all, but because there are no discrete luminous sources, and because neutral hydrogen blocks many wavelengths of light, preventing them from traveling long distances. The physical conditions during this period are simple in composition but subtle in structure. The gas is mostly hydrogen, some helium, and a trace of other light elements. It is nearly uniform on large scales, yet small fluctuations in density and temperature are already present remnants of earlier processes that stretched quantum fluctuations to cosmic size, and then imprinted them on the plasma. These irregularities are tiny in amplitude, but they are the seeds from which later structures will grow. Dark matter, which does not interact with light but responds to gravity, has already begun to cluster more strongly than the ordinary gas, forming a network of deepening potential wells. The neutral gas gradually falls into these wells, guided by gravity and moderated by pressure and cooling processes. During the Dark Age, the cosmic microwave background continues to cool and becomes less energetic. Its average temperature falls roughly in inverse proportion to the scale factor of the universe. At any given epoch, this background sets a thermal environment for the gas, influencing how atoms occupy their internal energy levels. One particularly important feature arises from the hydrogen atom. Hydrogen has a ground state with a subtle splitting between two configurations of the electron and proton spins. Transitions between these configurations produce or absorb radiation at a wavelength known as the hydrogen 21 centimeter line in later units. During the Dark Age and the subsequent period, when the first luminous sources form, this spectral line becomes a sensitive probe of the state of neutral hydrogen, its temperature, and its motion. In principle, by observing the sky at the frequencies corresponding to this line, red-shifted by cosmic expansion, radio telescopes can map the distribution of hydrogen across different epochs. This would turn the Dark Age, which emits almost no visible light, into a detailed three-dimensional data set accessible in radio waves. In practice, such observations are extremely challenging because the signals from hydrogen are faint and are masked by much stronger emission from the Milky Way and from human technology. Nevertheless, experiments are underway to detect the average signature of this line and its spatial fluctuations. Some early results have hinted at a possible absorption feature deeper than expected, suggesting that the hydrogen gas might have been cooler relative to the background radiation than simple models predict. If confirmed, such a deviation would point to additional processes at work, perhaps involving interactions between dark matter and ordinary gas, or the influence of the first sources turning on earlier than thought. For now, these hints remain under active investigation, showing how even small differences between data and theory during the Dark Age can open new possibilities for understanding unseen components of the universe. While the hydrogen signal awaits full mapping, other observations already constrain the later stages of this era. The cosmic microwave background, when examined in detail, bears the imprint of how matter clumped and how radiation traveled through these clumps. Slight distortions in the background's spectrum and angular structure arise from scattering off free electrons released during the later reionization of the universe, when the first luminous sources emit enough high-energy photons to ionize neutral hydrogen once more. By measuring the total amount of scattering that has occurred since recombination, scientists infer an approximate period during which reionization took place. This epoch of reionization is thought to begin when the first generation of stars and galaxies ignite and emit ultraviolet radiation that breaks apart neutral hydrogen, restoring a plasma in the surroundings of these sources. Over time, ionized bubbles grow and overlap, turning the universe from mostly neutral to mostly ionized again. The Dark Age thus has a finite duration. It is bounded on one side by recombination and on the other by the dawn of the first stars. Yet, within this interval, much of the groundwork for later structure is laid. The density fluctuations that were once small ripples grow under gravity, especially within dark matter halos. Some regions collapse earlier than others, forming dense knots where gas can cool and fragment. The timing of these collapses and the properties of the first stars that result depend on the initial fluctuation spectrum defined during inflation and on the detailed microphysics of gas cooling and chemistry in a mostly pristine environment. The first stars are believed to be massive, forming from metal-free gas that lacks efficient coolants beyond hydrogen and helium. Such stars would burn their fuel rapidly and end their lives in powerful supernova explosions, dispersing newly forged heavier elements into the surrounding medium. These explosions not only enrich the gas, but also drive shocks heat their surroundings and perhaps trigger further star formation. The radiation and particles they emit contribute to the ionization of the universe, gradually ending the Dark Age. Observationally direct detection of these first stars is extremely difficult because they form at great distances and live short lives. However, their collective influence may be visible in several ways. One is through the integrated light from many faint early galaxies, which contributes to the background in certain wavelength bands. Another is through the pattern of rionization imprinted on the hydrogen 21-centimeter signal. Yet another comes from the effect of early structure formation on small-scale anisotropies in the cosmic microwave background, including subtle secondary anisotropies produced when background photons scatter off moving electrons in ionized regions. Each of these channels carries partial information like overlapping shadows, hinting at shapes that cannot yet be seen clearly. The Dark Age also offers a kind of clean laboratory for testing cosmological models. Before the first stars ignite, physical processes are relatively simple. Gravity, atomic physics, and interactions with the background radiation dominate without the complication of astrophysical feedback from luminous sources. As a result, the distribution and evolution of hydrogen during this interval depends strongly on fundamental cosmological parameters, such as the amount and nature of dark matter, the total matter density, and the spectrum of primordial fluctuations. If future instruments can measure the 21-centimeter signal across many redshifts with high precision, they will provide stringent tests of these underlying quantities, complementing and extending the information from the cosmic microwave background and galaxy surveys. In theoretical work, models of the Dark Age often show that small departures from standard assumptions could leave clear imprints. For example, if dark matter particles occasionally scatter off ordinary atoms, they could cool the gas more efficiently, modifying the contrast between gas temperature and background radiation. If there were additional light particle species beyond known neutrinos, they could alter the expansion rate and the growth of fluctuations. If the inflationary period produced rare but strong features in the initial power spectrum, these could appear as unusual patterns in the hydrogen distribution. In this way, the quiet era between recombination and first light becomes a sensitive probe of physics at energies far higher than those accessible today. Yet despite its potential richness, the Dark Age remains largely unobserved directly. The main Confirmed signals from this period are still encoded indirectly in the cosmic microwave background and in the success of models that carry initial conditions forward into the era of galaxies. The absence of direct maps is itself an intriguing gap. It highlights how much of cosmic history is reconstructed rather than seen pieced together from later consequences. The expectation is that future radio observatories and space missions will gradually fill this gap, turning the Dark Age from an inferred stage into a measured one. When that happens, the quiet interval between the last scattering of the background photons and the first starlight may reveal not only how the universe prepared for the onset of complex structures, but also whether unknown processes were active in that seemingly simple time, leaving signatures that only careful observation can uncover. In this sense, the Dark Age is not merely an empty pause between more vivid chapters. It is a crucial link where the nearly uniform early universe evolves into a state ready to form stars and galaxies, and where subtle signals offer one of the most promising windows into both the cosmic past and the basic laws that govern it. As the Dark Age ends, the quiet gas of hydrogen and helium begins to organize itself under the influence of gravity and initial fluctuations. Small overdense regions, already amplified during the period of neutral gas, now become sites where the collapse of matter accelerates. Dark matter halos, which have been forming and growing since earlier times, provide the gravitational scaffolding. Ordinary gas falls into these halos' heats through compression and shocks, and gradually cools by emitting radiation. Where cooling is efficient enough to overcome pressure and turbulence, the gas contracts, further fragmenting into clumps that become the first stars. These earliest stars, often called population 3 stars in modern terminology, form from almost pristine gas without heavier elements. Without efficient coolants beyond hydrogen and helium, the gas tends to fragment into relatively massive clumps. As a result, the first stars are thought to be much more massive on average than typical stars that form later in chemically enriched environments. High-mass stars burn their nuclear fuel quickly and reach high temperatures in their cores. They emit intense ultraviolet radiation and live for comparatively short times before ending in powerful supernova explosions or collapsing directly into black holes. The radiation from the first stars begins to alter their surroundings almost immediately. High-energy photons ionize nearby hydrogen, carving out expanding bubbles of ionized gas around each star or cluster of stars. These bubbles grow and merge, contributing to the reionization of the intergalactic medium. At the same time, supernova explosions disperse heavy elements such as carbon, oxygen, and iron into the surrounding gas. This enrichment allows later generations of stars to form under different cooling conditions, leading to a broader range of stellar masses and more complex structures such as planetary systems. The onset of star formation marks a new phase in cosmic history. The universe, once dark and nearly uniform, now contains discrete luminous objects that shine across large distances. As more halos collapse and form stars, small galaxies assemble. These early galaxies are faint and compact compared to the large spiral and elliptical galaxies seen in the nearby universe, yet they play an outsized role in shaping the intergalactic medium. Their combined radiation field gradually transforms the universe from mostly neutral to mostly ionized again, except in the densest regions where gas remains shielded. Observations of distant galaxies with advanced space telescopes show that galaxies at high redshift are clumpy, irregular, and rapidly forming stars. Their light is redshifted by the expansion of the universe, moving ultraviolet and visible emission into the infrared range by the time it reaches Earth. Deep surveys that stare at small patches of sky for long periods reveal thousands of such young galaxies, each representing an early stage of assembly. Statistical studies of their abundances, luminosities, and clustering provide constraints on how quickly structure grew, how efficient star formation was in different halos, and how ionization proceeded. At the same time, the large-scale distribution of galaxies traces a pattern known as the cosmic web. On scales of tens to hundreds of millions of light-years, galaxies are not arranged randomly, but are found along filaments in sheets and in clusters, separated by vast empty regions called voids. This pattern matches in broad outline the expectations from the growth of initial fluctuations under gravity in a universe dominated by dark matter and dark energy. Numerical simulations that start from conditions derived from the cosmic microwave background and evolve dark matter and gas forward in time produce web-like structures that closely resemble the observed distribution of galaxies. The agreement between these simulations and large galaxy surveys supports the idea that small initial irregularities generated during the earliest epochs are sufficient to explain the complex structure of the present universe, when combined with known physics of gravity and gas dynamics. Yet within this apparent success, there remain tensions and open questions. On very small scales, such as the inner regions of galaxy halos and the counts of small dwarf galaxies around larger systems, discrepancies between simple dark matter models and observations have been noted. For example, pure dark matter simulations predict density profiles that rise steeply toward the centers of halos, while some observations suggest flatter cores in certain galaxies. They also predict more small subhalos than a number of dwarf galaxies detected around, for instance, the Milky Way. These issues may be resolved by including the effects of baryonic physics, such as gas outflows driven by supernovae, which can redistribute matter and alter halo structures, or they may hint at the need for refinements in the properties of dark matter. The precise nature of the first stars themselves is also not yet directly observed, while indirect evidence supports the idea of massive short-lived population. 3 stars, their exact masses, lifetimes, and yields of heavy elements remain uncertain. Future telescopes that can observe faint infrared light with high sensitivity aim to detect signatures of these first stars and galaxies more clearly, perhaps, by identifying characteristic features in their spectra, or by measuring the timing and patchiness of ionization with greater precision. The connection between early fluctuations and late structures is not limited to the distribution of galaxies. Subtle statistical features in the large-scale structures, such as the baryon acoustic oscillation scale, provide independent checks on cosmological parameters. These oscillations are the fossil remnants of sound waves in the early plasma, frozen into the distribution of matter when photons and baryons decoupled at recombination. The same scale appears in the cosmic microwave background as a pattern of peaks in the temperature-power spectrum. When measured in galaxy surveys, the baryon acoustic oscillation scale serves as a standard ruler, allowing the expansion history of the universe to be traced over time. The agreement between distances inferred from this method and those derived from other probes strengthens the overall cosmological framework, while also offering a way to test for deviations that might indicate new physics. Despite the broad consistency, some measurements of the expansion rate and the growth of structure show mild tensions when compared with the simplest models. For example, estimates of the current expansion rate based on nearby supernova and galaxies yield a value that is somewhat higher than the value inferred from the cosmic microwave background when interpreted within a standard cosmological model. Similarly, some measurements of the amplitude of matter clustering at intermediate redshifts differ slightly from simulation predictions. These differences are not yet large enough to demand a new paradigm, but they are persistent enough to motivate careful scrutiny of both data and theory. If they remain and sharpen with improved observations, they could signal a need to modify some aspect of the standard picture, perhaps in the behavior of dark energy, the properties of dark matter, or the physics of the early universe that sets initial conditions. The emergence of structure also raises questions about the long-term fate of galaxies and stars. Star formation consumes gas over time, and feedback processes from supernovae active galactic nuclei and stellar winds regulate how efficiently galaxies convert gas into stars. Observations show that the cosmic star formation rate rises from the earliest times to a peak a few billion years after the Big Bang and then declines. This history reflects the interplay between the supply of cold gas, the deepening of gravitational potentials, and the heating and expulsion of gas by energetic processes. The details of this evolution are sensitive to many parameters and processes, making galaxy formation a complex field in which cosmology and astrophysics meet. From the perspective of the early universe narrative, however, the key point is that the overall pattern of structure formation from the first stars and galaxies to the present large-scale web emerges naturally from the initial conditions inferred from the cosmic microwave background when evolved under gravity in a universe with dark matter and dark energy. The success of this broad picture is striking, yet the presence of small-scale discrepancies, unresolved aspects of feedback, and tensions in some cosmological measurements shows that the story is not complete. Seemingly minor mismatches can point to significantly new physics. Thus, while the emergence of stars and galaxies may appear as a straightforward consequence of gravitational collapse, it also serves as a sensitive test of the underlying cosmological model, tying the behavior of matter on scales of parsecs and kiloparsecs to the properties of the universe as a whole. In this way, the ignition of the first stars and the formation of structure are not only milestones in cosmic history, but also tools for probing the laws that govern the universe from its earliest moments. As measurements of galaxies and the cosmic microwave background improve, a striking fact becomes clear: most of the universe is made of components that do not shine. The visible stars, gas, and dust that make up familiar astronomical images account for only a modest fraction of the total matter and energy content. The rest reveals itself only through its gravitational influence and through the way it shapes the expansion of space. The first strong hints of missing mass appear in the study of galaxy clusters. When astronomers estimate the mass of a cluster from the motions of its galaxies, they find that the visible matter does not provide enough gravity to hold the system together. Galaxies move too fast to be bound by the mass of the luminous material alone. Later, rotation curves of spiral galaxies strengthen the case. Stars and gas in the outer regions orbit the galactic center at nearly constant speeds instead of slowing down, as would be expected if most of the mass were concentrated in the bright central regions. To explain these flat rotation curves, additional unseen mass is needed, extending beyond the visible disk in a roughly spherical halo. This non-luminous matter comes to be known as dark matter. Its presence is also felt through gravitational lensing, the bending of light by mass. Images of distant galaxies often appear distorted when their light passes near massive clusters or halos on the way to Earth. The degree of bending depends on the total mass, not just the light-emitting portion. By mapping these distortions, astronomers reconstruct mass distributions and find that much of the mass is invisible, spread out more broadly than the stars consistent with extended dark matter halos. The cosmic microwave background adds another layer of evidence. The pattern of temperature fluctuations across the sky, when analyzed statistically, encodes information about the relative amounts of ordinary matter, dark matter, and radiation at the time the background was released. Models that match the observed pattern require dark matter to account for a significant share of the total matter density, much more than the ordinary baryonic matter that forms stars and gas. Big Bang nucleosynthesis, which explains the observed abundances of light elements, also constrains the density of baryons. It shows that ordinary matter is too scarce to explain the gravitational effects seen on large scales. Together, these lines of evidence converge on a picture in which dark matter dominates the mass budget of the universe. Despite this, the nature of dark matter remains unknown. It does not emit, absorb, or reflect light in any appreciable way, and it interacts very weakly, if at all, with ordinary matter, aside from gravity. Candidate particles have been proposed ranging from relatively heavy, weakly interacting particles to very light, diffuse fields. Underground detectors search for rare collisions between dark matter particles and atomic nuclei. Particle accelerators look for signs of new particles that could play the role of dark matter. Astronomical observations test whether dark matter behaves as a simple cold pressureless fluid or has more complex properties. So far, no direct detection has been confirmed, and the simplest models, while remarkably successful on large scales, face challenges on the smallest scales where detailed galaxy structure is scrutinized. Alternatives to dark matter have been suggested, including modifications to the laws of gravity, at low accelerations or on large distances. These theories aim to explain galaxy rotation curves and some cluster dynamics without unseen matter by changing how gravity works. Some versions reproduce certain observations, but struggle to match the full breadth of data, especially the precise pattern of cosmic microwave background fluctuations and gravitational lensing maps. The current situation leaves dark matter as the leading explanation, but with an open invitation for new physics to clarify its true nature. As these questions about invisible matter are being explored, another even more surprising discovery arrives from studies of distant supernovae. Type 1, a supernovae which arise from white dwarf stars reaching a critical mass in binary systems, have relatively uniform peak brightness and can be used as standard candles to measure cosmic distances. By comparing the apparent brightness of such supernovae with their redshift, astronomers trace how the expansion rate of the universe has changed over time. Observations in the late 20th century reveal that distant supernovae are dimmer than expected in a universe whose expansion is slowing under the pull of gravity alone. The simplest interpretation is that the expansion of the universe is not merely continuing, but accelerating. This acceleration implies the presence of a form of energy associated with space itself, often modeled as a cosmological constant, or as a slowly varying field. This component, called dark energy, exerts a kind of negative pressure that drives accelerated expansion. In the framework of general relativity, such a component can be represented by a term in the equations that Einstein originally introduced to obtain a static universe and later set aside. In the modern context, a cosmological constant corresponds to a uniform energy density that does not dilute as space expands. As more space appears, the total amount of dark energy increases proportionally, maintaining a nearly constant density. Other possibilities involve dynamic fields whose energy density changes slowly over time. The existence of dark energy is supported not only by supernova data, but also by measurements of the cosmic microwave background, baryon acoustic oscillations, and the growth rate of large-scale structure. When all these observations are combined, a consistent picture emerges in which the total energy budget of the universe is dominated by dark energy with dark matter, providing most of the remaining share and ordinary matter, making up only a small fraction. In rough terms, ordinary baryons account for about 1 part in 20 of the total dark matter, contributes around 1/4, and dark energy fills the rest. These proportions are inferred in word and number, but their precise values are continually refined as new data arrive. The recognition that most of the universe consists of dark matter and dark energy raises deep theoretical challenges. Quantum field theory suggests that empty space should have vacuum energy density many orders of magnitude larger than the observed dark energy density. Reconciling this enormous difference is known as the cosmological constant problem. It is one of the most severe mismatches between theoretical expectation and measurement in modern physics. Various ideas have been proposed to address it, including mechanisms that cancel most of the vacuum energy or frameworks in which many possible vacuum states exist, with only those in which the effective cosmological constant is small enough, allowing the formation of galaxies and observers. None of these proposals has yet achieved universal acceptance. There is also the coincidence problem. The energy densities of matter and dark energy evolve differently over time, yet in the present era, they are of the same order of magnitude. In the early universe, matter dominates. In the far future, dark energy will dominate, strongly diluting matter to negligible influence on the expansion. That the transition between these regimes occurs during the epoch when galaxies and stars are abundant and observations are possible appears notable. Some view this coincidence as a clue that dark energy might not be a simple constant, but part of a more complex dynamical process. Others consider it a selection effect within a wider multiverse, where only in certain periods and regions does the balance of components permit rich structure. Observationally, dark energy is characterized primarily through its effect on the expansion history and the growth of structure. By mapping galaxy distributions, gravitational lensing and cluster counts across cosmic time surveys aim to measure how quickly the cosmic web grows and how distances scale with redshift. Any deviation from the pattern predicted by a simple cosmological constant could signal evolving dark energy or modifications to general relativity on large scales. Some current measurements show small discrepancies, such as tensions between the expansion rate inferred from the cosmic microwave background and that measured locally, or differences in the inferred strength of matter clustering. These may be due to unrecognized systematic errors, or they may be early indicators that the standard model of cosmology, while highly successful, is incomplete. The presence of dark matter and dark energy transforms the Big Bang from a story about visible matter into a broader narrative about components that do not interact with light, yet dominate the dynamics of the cosmos. The same expansion that reveals a hot origin and a rich history also exposes the limits of current understanding. The instruments that map the sky from radio arrays and optical telescopes to space-based observatories sensitive to microwaves and infrared have built a coherent picture in which the large-scale behavior of the universe is described by a small set of parameters. These include the densities of ordinary matter, dark matter, and dark energy, the amplitude and spectrum of initial fluctuations, and the overall geometry of space. Yet, behind each parameter lies a question: what physical entities and mechanisms do these numbers represent, and why do they take the values they do? In this sense, the discovery of cosmic acceleration and the inference of invisible ingredients do not close the book on the Big Bang. Instead, they show that the beginning and evolution of the universe are governed by elements that are still only partially understood. The accelerating expansion ensures that distant regions will eventually recede beyond observational reach, while local structures bound by gravity remain. The universe grows larger and emptier on the grandest scales, even as the fundamental questions about its unseen contents remain among the most active topics of research. The early clues embedded in galaxy rotation curves, lensing maps, supernova light curves, and the microwave background have opened a long path of investigation into the dark components that shape cosmic history, from the first instance to the far future, revealing that the visible universe is only a small window onto a much larger and more mysterious whole. As the picture of cosmic history sharpens, the most elusive part of the story remains the very beginning. The hot Big Bang framework, combined with inflation and well-tested physics, describes the universe convincingly from a very early time onward, but it does not fully explain how the initial state itself arose. Extrapolating the expansion backward using classical general relativity leads to a singularity, a moment when densities and curvatures become infinite and the equations lose their predictive power. This singularity is widely interpreted not as an actual physical object, but as a sign that the theoretical tools being used are incomplete. At times, earlier than a tiny fraction of a second after the start, when conditions approach the Planck regime of extreme density and very small scales, a theory that unifies general relativity with quantum mechanics is expected to become essential. Candidate frameworks for such a quantum theory of gravity exist, but none has yet been confirmed experimentally, and each offers a different perspective on what, if anything, lies before the hot Big Bang phase. One class of ideas imagines that the Big Bang is not the absolute beginning of time, but a transition from a previous phase. In some bouncing cosmologies, the universe contracts from a large cold state, slows as matter and radiation become denser, and then undergoes a bounce that reverses the contraction into expansion. The bounce might be triggered by quantum gravity effects that prevent densities from becoming truly infinite, or by exotic forms of energy that behave differently at extreme conditions. In these scenarios, the hot Big Bang represents the aftermath of a prior collapse, and traces of the pre-bounce universe might be imprinted in subtle features of the cosmic microwave background or in the distribution of primordial fluctuations. Variants of this idea, such as ekpyrotic models, draw inspiration from higher dimensional theories, where our universe is a three-dimensional brain embedded in a larger space. Collisions between brains could, in this picture, generate bursts of energy that appear as Big Bang events in each brain, possibly repeating in cycles over very long timescales. These models aim to explain not only the existence of a hot beginning, but also the near flatness and uniformity of the observed universe, as well as the origin of fluctuations without relying on traditional inflation. They predict different detailed patterns in the primordial fluctuations and careful analysis of data from the cosmic microwave background, and large-scale structure has been used to test them. So far, the simplest versions of ekpyrotic and cyclic models are constrained strongly by observations, but the general approach remains an active area of exploration. Another line of thought considers emergent universe scenarios in which the universe exists in a quasi-static or slowly evolving state for an extended period before entering a phase of rapid expansion that resembles inflation. In such models, there may be no initial singularity in the conventional sense. Instead, the universe could have an infinite past, in which its properties change very gradually, with the hot Big Bang marking a transition from one regime to another. This notion avoids some conceptual issues associated with a finite beginning, but it shifts the question to why the emergent phase exists and how it becomes unstable, leading to expansion. Quantum cosmology approaches, which attempt to apply quantum principles directly to the universe as a whole, offer further possibilities. In some treatments, the universe is described by a wave function that encodes all possible configurations of geometry and matter. Time may not appear as a fundamental parameter, but emerge from relations between different parts of the system. Proposals have been made in which the universe tunnels from a state with no classical space-time into one where space and time are well defined, or where the boundary between past and future is described in terms of a compact geometry without a singular point. In such pictures, asking what happened before the Big Bang may be similar to asking what lies north of the geographic North Pole. The question presumes an extension of concepts beyond the domain where they apply. These ideas are mathematically rich, but face significant challenges in connecting to observable consequences. Eternal inflation offers yet another perspective. In many inflationary models, the field that drives rapid expansion decays in some regions, ending inflation locally and seeding hot Big Bang phases, while in other regions it continues to inflate. The result is a multiverse of bubble universes, each forming where inflation ends embedded in a larger inflating background. Within each bubble, the conditions may be similar to or different from those in others, depending on how the underlying fields and physical constants behave. Our observable universe would then be one such bubble with its particular values of parameters like the density of dark energy and the strengths of forces determined either by local physics or by a broader landscape of possibilities. In this framework, the Big Bang is a local event, not the origin of all reality, and there may be no single global beginning. The concept of a multiverse also arises in some approaches to quantum gravity and string theory, where the space of possible vacuum states is large. Different regions of the broader structure could inhabit different vacua, each with its own effective laws of physics. Observationally, such a multiverse is difficult to test directly because regions beyond the observable horizon are causally disconnected. However, certain rare events, such as collisions between bubble universes in an inflationary multiverse, might leave faint imprints on the cosmic microwave background or other observables, although no convincing evidence for such signatures has been found so far. The idea that the observed values of cosmological parameters might be selected by the requirement that galaxies and complex structures conform is sometimes used to reason about why the cosmological constant is small, or why the matter density has its observed value. This anthropic reasoning does not provide a dynamical explanation, but offers a possible statistical perspective if a vast ensemble of universes exists. It remains controversial as it is difficult to falsify and blurs the line between physics and broader interpretation. In all these speculative scenarios, empirical constraint is the crucial guide. The cosmic microwave background, with its precision measurements of temperature and polarization, already rules out many specific early universe models by not showing certain predicted features. Large-scale structure surveys, gravitational wave detectors, and future probes of the dark age through hydrogen mapping may further narrow the space of possibilities. Some models predict distinct patterns of primordial non-Gaussianity in the fluctuations or a specific spectrum of primordial gravitational waves or subtle departures from the simplest inflationary predictions. The absence or presence of such signals in upcoming data will help to distinguish between competing narratives of the very beginning. There are also proposals in which black holes and cosmology are linked more directly. In some speculative frameworks, the interior of a black hole could be connected to the birth of a new expanding region of spacetime, so that each black hole might seed a baby universe. If such processes occur, the laws and constants in the offspring universe could differ slightly from those in the parent, leading to an evolutionary picture where universes that produce many black holes have more descendants. This idea, sometimes called cosmological natural selection, attempts to apply evolutionary reasoning to the space of possible universes, with black hole production playing a role analogous to reproductive success. Although intriguing, such notions remain highly speculative and face serious challenges in formulating clear, testable predictions. Across these diverse attempts to look beyond the hot Big Bang, a common pattern emerges. Known physics describes the universe well from a very early time onward, and observations strongly support this description. However, as one pushes closer to the notional beginning, the assumptions underlying classical space-time and standard quantum field theory begin to break down. Theories that extend or replace these frameworks introduce new structures and mechanisms that could, in principle, explain why the universe has its observed properties. Yet, without decisive observational signatures, they remain possibilities rather than established facts. The question of whether the universe had an absolute beginning, whether time extends infinitely into the past, or whether our observable region is one of many in a larger multiverse, remains open. Current data constrain the range of viable models, but do not pick a unique story. New instruments and observations may reveal subtle clues in the cosmic microwave background, in the distribution of galaxies and hydrogen, in the behavior of gravitational waves, or in rare particle processes that point toward one class of scenarios over others. Until then, the earliest moments of the universe stand as a frontier where well-tested science meets carefully disciplined speculation. The Big Bang, in this view, is not a single exploding point, but a transition in the behavior of space-time and energy whose deeper origin is still under investigation. The observable universe, with its galaxies, stars, planets, and living beings, is one expression of whatever broader reality underlies space and time. The evidence gathered so far outlines a detailed sequence from a hot, dense state to the present cosmos. But the ultimate reasons why this sequence exists, why the initial conditions took the form they did, and whether other forms are realized elsewhere in a wider landscape, remain open questions inviting further inquiry as instruments become more sensitive and theories more refined. In the present era, the universe stands between its dense, hot origin and its distant, colder future. Galaxies thread a vast cosmic web, stars burn quietly, or in bursts, planets circle in stable paths, and on at least one world living systems have arisen that can look outward and piece together a story extending back to the earliest observable moments. From background radiation measurements, from the motions of galaxies, from the abundances of light elements, and the distribution of large-scale structure, a coherent account emerges. Space has expanded from a much hotter and denser state. Matter has separated from radiation, forces have differentiated, and small initial fluctuations have grown into the intricate patterns now seen. This account is detailed and quantitatively successful, yet it is not complete. The nature of dark matter and dark energy remains unknown. The exact mechanism that produced the tiny excess of matter over antimatter is still under investigation. The unification of gravity with quantum mechanics and the true character of the earliest instance lie beyond current experimental reach. Even the possibility that the observable universe is one region within a larger structure, perhaps with different physical conditions elsewhere, remains open. In this sense, every firm result frames new questions. The measured pattern of microwave anisotropies points back to processes that shaped primordial fluctuations but does not uniquely identify their origin. The acceleration of cosmic expansion reveals the influence of dark energy, but does not yet explain its magnitude or nature. The success of the standard cosmological model in reproducing many observations coexists with small tensions and anomalies that may be statistical, systematic, or hints of new physics. Future instruments will reduce uncertainties and perhaps uncover new signals. Faint gravitational waves from the early universe, detailed maps of hydrogen in the Dark Age, sharper measurements of structure growth and expansion history. Each new observation will either reinforce the existing framework or force revisions that bring theory closer to whatever reality underlies space-time, and energy. For now, the universe presents itself as a system whose broad evolution can be traced from an early hot phase to the present, but whose ultimate origin and full extent remain uncertain. The same laws that allow a clear reconstruction of many steps also mark a boundary beyond which current understanding cannot yet pass. In that boundary region between what is measured and what is still conjectured, the story of how the universe began remains open, inviting further observation, calculation, and reflection as the cosmos continues its expansion into the unknown.